Hey everyone and welcome. Look, if you're trying to absolutely lock down your board exam chemistry scores, you are in the exact right place today. This explainer is a rapid, highly focused chemical kinetics masterclass. We're stripping away all the fluff and just getting straight down to the high-yield material. Whether you studied this chapter a dozen times already or, you're just opening your books right now, by the end of our time together, you're going to know exactly what concepts and numericals are practically guaranteed to earn you marks. So get focused, grab a notebook if you need to, and let's just get straight into it.
So here's our roadmap for this explainer. First up, reaction rates and rate law. Second, order of reaction explained. Third, zero and first order formulas. Fourth, we'll be solving a board numerical. And fifth, final exam tips.
Section 1. Reaction rates and rate law, the core engine of kinetics.
Imagine you're driving a car, right? Your speed is measured in miles or kilometers per hour. Well, in chemistry, the speed of a reaction is the rate of reaction. It's simply defined as the change in the concentration of any one reactant or product per unit time. As your reaction actually progresses, your reactants are dropping and your products are rising. And please, absolutely burn this unit into your memory, moles per liter per second. That is the speedometer of our chemical reactions, and knowing that specific unit is an absolute must for your exams.
Now, here's where we introduce a really crucial twist. The rate law. You might think you can just look at a balanced chemical equation, A plus B gives some product, and instantly know exactly how the rate behaves just based on the coefficients. But you can't. It's kind of like baking a cake where the recipe on the box completely lies to you about how much flour you actually need. The rate law is an expression of the reaction rate in terms of reactant concentration powers, and here is the major trap. Those powers may or may not match the balanced equation's stoichiometric coefficients. You literally cannot figure out the rate law just by looking at a piece of paper. It is a purely experimental concept. This definition alone has shown up as a 2-mark question in board exams, so make sure you've got it down cold.
Moving on to Section 2. Order of reaction explained. Calculating the exponents.
So the absolutely crucial point here is how we actually calculate this order. If you look at an experimental rate law, you'll see your reactants raised to certain powers. The order of reaction is literally just the sum of those exponents. So if reactant A is raised to the power of 2 and reactant B is raised to the power of 3, the overall order is simply 2 plus 3, which equals 5. And because the rate law is an experimental concept, the order of reaction is strictly experimental too. Don't be surprised by the numbers you get here. It can be a whole number like 1, 2, or 3, but it can also be 0, which just means the rate doesn't care about that reactant's concentration at all. It just proceeds at its own pace. It can be a fraction or even negative. And negative is wild because that means adding more of that reactant actually slows the reaction down.
Section 3. Zero and first order formulas. The essential math.
Okay, this perfectly illustrates exactly what you need to memorize. Let's contrast these side by side. For a zero-order reaction, the rate constant K equals the initial concentration A0 minus the final concentration A, all divided by time t. Its half-life, the time it takes for exactly half the reactant to be consumed, is simply A0 divided by 2K. But look over to the first-order side. This is where examiners love to test you. The formula changes significantly because it introduces logarithms. For first order, K equals 2.303 divided by T, multiplied by the log of initial concentration over final concentration. And the half-life? That simplifies beautifully to 0.693 divided by K. Notice how the first-order half-life formula doesn't even have an A0 in it. It is completely independent of the initial concentration. Fun fact, every single radioactive decay process in the universe follows this exact first-order math. Keep these equations locked in your brain because we're about to use them.
Section 4. Solving a board numerical, 50% to 80% completion.
Here is a very real high-probability problem. A first-order reaction takes 69.3 minutes for 50% completion. How long will it take for 80% completion? Now, I want you to mentally map this out for a second. We're given one scenario, the 50% completion, and we need to use that to find the secret key, the rate constant K. Once we have K, we can unlock the second scenario to find the time for 80% completion.
Let's meticulously walk through this math together. Step 1. Let's assume our initial concentration, A0, is a perfect 100. If the reaction is 50% complete, what's our remaining concentration A? Well, it's 50. So using our first-order formula, we plug in our time of 69.3 minutes. We get the log of 100 over 50, which is just the log of 2.
Step 2. We calculate our rate constant K. The log of 2 is roughly 0.301. When you multiply 2.303 by 0.301, you magically get exactly 0.693. So our equation becomes K equals 0.693 divided by 69.3. Do that quick math, and K equals 1 over 100, or 0.01. That is our intermediate key, step 3. Now we tackle the 80% completion. Again, A0 is 100. But here is the critical trap that catches literally so many students. A is the remaining concentration. If 80% is complete, how much is actually left behind? Exactly 20. So we're doing the log of 100 divided by 20, which gives us the log of 5. Step 4, we plug our K of 1 over 100 right back into the formula. Time T equals 2.303 divided by 1 over 100 times the log of 5. The log of 5 is about 0.698. Multiply it all together, 2.303 times 100 times 0.698, and you get a final time of approximately 161 minutes. Boom. If you can follow that logic, you have just mastered one of the absolute toughest types of numericals this chapter is going to throw at you.
And finally, Section 5, Final Exam Tips, securing your 3 marks.
Here is my absolute warning to you before we wrap up. A 3-mark numerical from chemical kinetics is virtually guaranteed on your board exams. It's inescapable. You simply cannot just read the theory and hope for the best. You must put pen to paper and actually practice the math. What we just did with first-order reactions is incredibly high yield. But there's another half to this puzzle. Once you're comfortable with concentrations over time, your very next focus absolutely must be activation energy. It's like a ball rolling up and over a hill. That initial energy push, you need to get it over the top, that is exactly your next focus.
Which leaves us with this final thought. You've just mastered how concentration changes dictate the clock of a chemical reaction. But what happens when you turn up the heat? How does temperature literally ignite that rate? And what invisible energy barriers do these molecules have to completely smash through just to react? I highly urge you to keep this momentum going. Dive into your textbooks and practice those numericals. Understanding kinetics doesn't just pass exams, it seriously unlocks the fundamental pacing of the universe. So what invisible energy barriers will you smash through next? Thank you so much for joining this explainer, and keep studying hard.